This is the first talk about basic electronics. The purpose of this talk is to explain the math and principles required for calculating voltage, current, resistance, and watts in single resistor circuits using direct current, and to serve as an introduction to electrical circuits in general. To understand the math and principles required for the calculation of the different values in single resistor direct current circuits, it is helpful to present all elements of the circuit with symbols. The international symbol for resistor is a featureless rectangle with two terminals extending outwards. The symbol for resistor in the United States is a zigzag line or a squiggle, also with two terminals extending outwards. For the purpose of this talk, we will use the symbol for resistor used in the United States. Electricity for the single resistor in a direct current circuit is supplied by a battery. The label often used to refer to direct current is DC in capital. A good place to start to understand single resistor direct current circuits is to create a master slide, and a good place to start creating such a slide is considering current and all the relevant factors involved with it. So we will have to consider electrons, charge that is represented by the letter Q, coulombs that is represented here by the letter C, amperes that is represented by the letter A, voltage that is represented by the letter V, capital, and resistance that is represented by the Greek capital letter omega. Next, we have to consider resistance. Factors involved with resistance are resistance itself, current, and voltage. Next, we have to consider electromotive force. Factors involved in electromotive force are voltage, ampere, and resistance. And finally, we have to consider power. Factors involved in power are coulombs, watts, that is the unit of power and is represented by the letter W, joules, which is the unit of energy and is here represented by the letter J, ampere, voltage, and resistance. In addition to the master slide, we need to know two laws. The Ohm law, which we will shortly analyze following the magic triangle for Ohm law, and the Joule's law, which we'll also analyze using the magic triangle for Joule's law. And finally, we have to consider and understand two concepts. Both concepts are related to single resistor direct current circuits. One of these concepts is voltage source and the other is voltage drop. From this point on, this talk will be conducted in a question and answer format. The first question is: just look at this figure and decide which one is the symbol for a resistor. In this frame, I will introduce all symbols matching with their names. First is the resistor, second, the amplifier, third, a capacitor. Notice that both vertical lines are the same length and that one of them is curved, and the battery. So the answer to this question, which I'm sure you know, especially if you were paying attention to the beginning of this talk, is A. The next question is: a resistor is an active circuit element. A, true, B, false. Circuits are constituted by wires and elements. Wires, when building the diagram for a circuit, are considered as having no resistance and not to add power to the circuit. Hence, wires do not subtract or add value to the circuit. They are represented by a line. Elements can be passive. Passive elements dissipate or store power in the circuit. Examples of passive elements are resistors and capacitors. Active elements, on the other hand, add power or amplify voltage. Examples of active elements are batteries and amplifiers. Often during this talk, I will tell you about analogies. But a word of caution: electricity is unlike anything else we know, so analogies help to understand certain specific aspects of it, but often confuse others. I know of no one analogy that is good to explain all the qualities of electricity. Having said this, I am going to use an analogy to explain passive and active elements. In this frame, I have drawn a mountain with a river and a lake at both ends. Here I added a power plant delivering electricity to the little house representing a hospital. This is the same drawing I so often use when talking about electrical safety. I have added a water tank that is dropping water into the river. In this drawing, the turbine in the river is a passive element. The water tank is an active element, not because it is adding water, but because it is adding kinetic energy, that is, the force of the water as it drops into the river. So the answer to this question is B, false. The next question is: in which direction electrons travel in direct current circuits? A, in a counterclockwise direction. B, from the small end of the battery symbol. C, opposite to current. D, all of the above. I'd like to start elaborating an answer to this question by presenting to you the master slide we built at the beginning of this talk. The purpose of this question is to cone our discussion to direct current, specifically as it relates to movement of current and electrons. Electrons in a direct circuit travel in a counterclock direction. They are depicted as arising from the shorter of the lines representing the negative pole of the battery. Current, on the other hand, is represented as traveling in the opposite direction than electrons. Current in a circuit travels in a clockwise direction. Of course, this unidirectional movement of electricity refers to direct current. It is important to stress that the convention that links the direction of electron and current flow to the direction of the movements of the clock hands is not accepted by all. And what is most consistently followed is that electrons flow away from the smaller horizontal line and current flows away from the longer horizontal line. So the answer to this question is D, all of the above. The next question is, blank is a unit of charge, parenthesis Q, A ohm, B volt, C ampere, T coulomb. I like to start elaborating an answer to this question by asking you to look at the master slide we created. As you can see, so far we have discussed direct current, and electrons. The purpose of this question is to introduce the symbol for charge, which is Q. Introduce the symbol for the unit of charge, that is coulomb, and explain their nature. First, we must consider the single electron. One electron, here represented as a red dot, has one negative charge. And a single proton, here represented as a blue dot, has a positive charge. Their charges, that is the charge of an electron and a proton, are equal and opposite, and they attract each other. The unit used to measure this attraction is the coulomb. 1 coulomb represents the attraction of 6.24 to the 18th power of 10 electrons. I will represent 1 coulomb as 1 magenta dot. I will tell you another analogy, but before telling it, I will warn you about one more thing regarding analogies. Analogies are very personal. What makes sense to some do not make sense to others. In this case, I will use a romantic analogy that makes sense to me, and I hope that it makes sense to you.
Think of electrical attraction as the longing of an electron, represented in this frame by the red half of the heart, for a proton, represented here by the other half of the heart, painted in blue. This longing, when generated by a large number of electrons, as you can see here, pointed by the arrow, is called, as you know, a coulomb. That, as we have done in the past, will be represented by a magenta dot. So the answer to this question is D. The next question is, the coulomb was named after a French physicist. A, true. B, false. Take a moment to read the statements in this frame. I find it amazing that despite the crude instruments Charles Coulomb had to work with, he was able to be so precise. Notice that this statement was written in 1785. The answer to this question is A, true. Next question. Blank is the unit for movement of charges. A, ohms. B, volts. C, ampere. D, coulomb.
I like to start elaborating an answer to this question by asking you again to look at the master slide. Already we have discussed direct current, electron, charge, and coulombs. The purpose of the current question is to introduce the symbol for ampere and explain its nature.
So coulomb is the unit of attraction. Attraction is a force as depicted in the last analogy. The unit that relates attraction, specifically the attraction in a conglomerate of 6.24 to the 18th power of 10 electrons to time, that is to seconds, is the ampere. The ampere is the unit used to tell the number of coulombs passing through a point in a wire each second. 1 ampere is equal to 1 coulomb passing through a point in a wire in a second. I will give you an example. Let's say that the yellow cylinder is a wire. The blue arrow indicates a point in the wire. The stopwatch is in milliseconds. It is there to represent time. Now I have added the coulombs. As you can see, they are numbered, and so far none has gone through the point in the wire signaled by the arrow. 1 millisecond has gone by in this frame, and 1 coulomb has passed the point selected. Now 250 milliseconds have gone by and 5 coulombs have passed the point. Now 500 milliseconds have gone by and 9 coulombs have passed the point. Now 750 milliseconds have gone by and 12 coulomb have passed the point. Now 900 milliseconds have gone by and 16 coulombs have passed the point. Now 1000 milliseconds, that is 1 second, has gone by and 20 coulombs have passed the point indicated by the arrow. We can thus say that the current going through in the wire is 20 coulombs every second, or 20 amps. So recapping what we have just heard, one electron has one negative charge. 1 coulomb has the charge of many electrons. And 1 ampere is 1 coulomb going through a point in a wire, which we can think of as a door, each second. So the answer to this question is C, ampere. Next question. The ampere is a unit of current. A true, B false. The ampere was named after this man. The ampere is the unit of current, that is coulombs per second. So the answer to this question is A. Next question. Blank is a unit for electromotive force. A ohm, B volt, C ampere, D joule.
Again, I am going to ask you to look at the master slide. So far, we have already discussed direct current, electron, charge, coulombs, and ampere. The purpose of this current question is to introduce the symbol for volt. I will provide an explanation about the nature of volt in a few minutes, but not linked to this question. Volt is the unit of electromotive force. We can think of volt as to what makes the electron move in one direction.
The unit was named after an Italian physicist. So the answer to this question is B, volt. Next question. 1 volt is the force needed to move 1 ampere against a resistance of 1 ohm. A true, B false.
1 volt is the force needed to move 1 ampere, that is 6.24 times 10 to the 18th power every second in a wire with a resistor equivalent to 1 ohm.
So the answer to this question is
A, true.
Next question. Blank relates to electrical resistance. A ohm, D volt, C ampere, D joule.
Once again, I like to start elaborating an answer to this question by asking you to look at the master slide. As you can see, we have already discussed current, direct current, electron, charge, coulombs, amperes, and volts. The purpose of this question and those following is to introduce the symbol for resistance and to explain its nature.
The electrical unit related to the resistance of the movement of charges is the ohm. The unit was named after a German physicist. The answer to this question is A. Ohms. Next question. Ohm's law can be represented by all of the following formulas except A, E equals I times R, B, I equal E divided by R, C, R equal E divided by I, D, R equal I divided by E. The purpose of this question is to introduce a law needed to understand single resistor direct current circuits. This is the law of Ohms. If we look at the last three symbols related to current and then look at the rest of the frame, we can find that these three symbols repeat when analyzing resistance. They also repeat when analyzing electrical force, and they also repeat when analyzing power. This pattern of repetition speaks volume about the importance of knowing how and when to use this law. This is a painting of Volta explaining Ohm's law to Napoleon. As you can see on your right hand side, a man was writing the explanation. Since I could not find it, I will tell you the best one I know. I use, in order to explain Ohm's law, the magic three-compartment triangle. The top compartment is for the letter E. It stands for electromotive force. On the left side, on the lower compartment, is the letter I. The letter I stands for current. In the next compartment is the letter R. R stands for resistance. Each of these compartments of the magic triangle have different units. The unit for current is the ampere, usually referred to as amp or simply by the letter A. The unit for electromotive force is volt, often referred just by the letter V. And the unit for resistance is ohm, usually indicated by the Greek capital omega. Using the magic triangle is easy. Just cover the compartment you want to determine and execute the operation suggested by such a maneuver. Let's say you want to find the electromotive force of a circuit. Cover the letter E and then execute the operation. In this case, it will be E equal to I times R. Let's say now you want to determine the value of current. You cover the letter I then you execute the operation. In this case, I is equal to E divided by R. Let's say you want to find out resistance, then you cover the letter R and execute. R is equal to E divided by I. So the answer to this question is D. Now that we have completed the triology amp, volt, and ohms, I like to bring in another analogy. An electron is always moving in its orbit and always have a negative charge. I think of the electron and its charge moving in their orbits as a young man running in place with his backpack. I have introduced in this frame two things: fire and wind, and I have changed the position of the young man. The storyline that goes with this frame is that when the young man's backpack catches fire, he starts to run forward to avoid being burned by the flaming backpack. And his way forward is opposed by the wind in his face. The fire in this frame represents the volts and the wind represents ohms. At the end, when the fire gets extinguished, the young man starts again to run in place and there is no longer wind against his face, similar to what happens when volts are no longer present to propel electrons to move in one direction, that no longer is resistance present. The reason we talk about charges and not about electrons is because the only way we have to detect an electron is by detecting the charge signatures it produces. The important point to take out of this last frame is that charges are not spent during the directional movement of electricity. Volts are. So how do amps fit in this analogy? The amps represent many electrons with their charges, to be exact 6.24 to the 18th power of 10, that propelled by volts and delayed by ohms cross the finish line within 1 second. I like to stress at this point that out of the three factors involved in Ohm's law, only amps is related to time. Neither volts or resistance has a time factor. Next question. Commonly used voltage sources are batteries and electrical wall outlets. A true, B false. The purpose of this question is to introduce one of the elements that is constantly present in all resistor circuit, that is voltage source. Even in the simplest of resistor circuit, the single resistor direct current circuit, there must be a voltage source. A voltage source will also be present in resistor circuits involving alternating current. Batteries are a voltage source, and so are wall receptacles. Electrical receptacles are another name for electrical wall outlets. So the answer to this question is true, A.
Next question. Batteries have volts on the side from where electrons flow and no volts on the other side from where current flows. A true, B false. I'd like to start answering this question as I have done in the past by asking you to look at the master slide and focus on the words and symbols with the blue background.
The electromotive force of a battery can be measured by a voltmeter. A voltmeter can be connected to the battery any way we want. For our understanding of electricity, it's best to connect the blue probe to the negative pole, the anode, and the red probe to the positive pole, the cathode. Such an arrangement gives us a positive value. The implication is that there is a difference, in this case of 10 volts, between the two poles. The value of this arrangement is best perceived if we draw a diagram. As you can see in this frame, the symbol of a battery is being measured by a voltmeter. The negative pole, the anode, has 10 times more volts than in the positive side, the cathode, which has none. So the answer to this question is A, true. Next question. Once a 12-volt battery releases 12 volt, it is dead. A, true, B, false. Batteries steadily release volts. A 12-volt battery can be thought as containing many 12-volt packages. These packages are released over time, one package at a time. This is expressed in this frame by the T1, followed by another package expressed by T2, representing time, and another the following time, that is T3. And so until the battery is finished. So the answer to this question is B, false. Next question. The anode of a battery has more electrons than the cathode. A, true, B, false. The distribution of volts, electrons, and charges in a battery requires some explanation. The distribution of volt is not equal between the negative and the positive poles of the battery. In this frame, we are representing 10 volts on the negative side and no volts on the positive side of a battery. Electrons are equally distributed on both poles. Charges are also equally divided. So the answer to this question is false. Next question. The voltage difference across a given resistor is known as a voltage drop. A, true, B, false. We have already talked about voltage source. I will now talk to you about voltage drop. By connecting a voltmeter to sense first the electricity coming into the resistor and then the electricity coming out of the resistor, the voltmeter will sense more volts coming in than going out. This will be reflected in the voltmeter screen by a -10. Yet, the number of electrons and charge represented by the letter Q at the entrance of the resistor and at the exit of the resistor are the same. In this frame, before leaving the subject, I am introducing the classic definition of voltage drop. Take a few seconds to read it. So, the answer to this question is A.
Next question. What is the voltage in the upper rail of the circuit below? A 18, B 6, C 0. If we use a voltmeter connected to the upper and lower rails of this circuit, we would get a reading of 18 volts. This implies that the volts in the upper rail is 0 and the volts in the lower rail is 18. So the answer to this question is C. Next question. What is the voltage drop across the resistor? A 18, B 6, C 0. If we use the voltmeter again to probe into the two terminals of the resistor in the same fashion as we have done before, the result will be 18 volts. 18 volts will be present where the electrons go in the resistor, and 0 volts will be present where they go out. So the answer to this question is A. Next question. What is a unit of power? A true, B false. I will once again go to the master slide to start answering this question. I chose to talk about watts when talking about power before talking about joules because I find watts easier to understand than joules. Hence, the first question about power refers to watts. If you recall, at the beginning of this talk, I told you about the importance of two laws: the Ohm law and Joule's law. We have already discussed Ohm law, so I will now talk about Joule's law. I have always found it interesting that Joule's law does not include joules as a unit in any of its terms. It is probably for this reason that Joule's law is often referred to as the power law. Be it as it may, the unit for power, as we previously mentioned, is watts. It was described by James Watt, Scottish mechanical engineer. So the answer to this question is A, true. Next question. Joule's equation states all of the following except A, P is equal to E times I, B, E is equal to P divided by I, C, I is equal to E divided by P, D, I is equal to P divided by E. I will use the magic triangle for Joule's law to explain it. As all magic triangles related to electricity, it has three components. The top component is occupied by the letter P. P stands for power. The lower component to your left is occupied by the letter I. I stands for current. The last component is occupied by the letter E. E stands for electromotive force. The unit for power is the watt. The unit for current, the amp. The unit for electromotive force is volt. Now the question is how to use the triangle. And in a way, we use it much like we have used the triangle when we talked about Ohm's law. We cover the factor that you want to find out and then execute the mathematical operation suggested by covering the factor in question. So if we want to know the value of P, we cover P and then execute, which would be that P is equal to I times E. If instead we want to know the value of I, we cover I and execute the suggested operation, which is I is equal to P divided by E. If, on the other hand, we want to find out the value for E, we cover E and then execute the operation, which will be E is equal to P divided by I. So the answer to this question is C. Next question. Joule's equation states all the following except A, P is equal to I to the second power times R, B, P is equal to B to the second power divided by R, C, P is equal to I to the second power divided by R, D, P is equal to E times I. Joule's law, as Ohm's law, has many versions. If we start with power as being equal to electromotive force times current and choose to work with E, which stands for electromotive force, And recall from the Ohm's law that electromotive force is equal to current times resistance. We can then substitute E by I times R and simplify the equation to express that power is equal to I to the second power times resistance. On the other hand, if we choose to work with I, and again recall Ohm's law that states that current is equal to electromotive force divided by resistance, thus we can represent P as electromotive force times the result of the division of E and R, which can further be reduced to E to the second power divided by R. So, when asked how many watts are in a circuit, we can use any of the equations that we have introduced. We can use the equation which states that power is equal to electromotive force times current. If you work it out using this equation, the diagram shown in this frame will have 108 watts. If instead we use the version substituting E, which it would be that P is equal to I to the second power times R, the result again will be 108 watts. And of course, if we use the version achieved by substituting I, which is P is equal to E to the second power divided by R, the answer will still be 108 watts. So the answer to this question is C. Next question. A joule can be defined as the energy needed to separate 1 coulomb against an electrical potential of 1 volt. A true, B false. I like to start answering this question once again by asking you to look at the master slide. I have done this over and over because I want you to have a global picture in your mind as to what is it that we're doing with all these questions. In relation to power, we have already discussed watts. So now it comes one of the hardest things, I think, in understanding electricity, and that is the definition of joules. I think the reason the definition of joules is so hard is because joules can be defined using multiple factors. I will put forward 4 definitions of joules. The first definition is the biological definition, which, as a matter of fact, is the simplest. The energy in 4.184 joule is equal to the energy in 1 calorie. Next, I will put forward the definition of joules in Newtonian physics. From a kinetic energy point of view, we can define a joule as the energy needed to accelerate a body with a mass of 1 kilogram for a distance of 1 meter at a velocity of 1 meter per second every second. From the electrical point of view, we can define 1 joule as the energy required to keep 1 coulomb of charges apart when being pulled together by 1 volt. A fourth definition of joules also involves electricity. It states that a joule is the energy expended by 1 watt of power in 1 second. More simply stated, 1 watt is equal to 1 joule per second. So the answer to this question is true. Next question. A resistor produces heat in exchange of current. A true, B false. Resistors produce heat without producing any reduction in current. Resistors produce heat as they consume volts. To illustrate this point, I will use another analogy. The amount of water in a river before and after a turbine of an hydroelectric plant is the same. The water above the turbine has high kinetic energy. The water below the turbine has a low kinetic energy. In this situation, the kinetic energy has been removed by the turbine and transformed into electricity. So the answer to this question is B, false. Next question. How many joules will be spent by a light bulb of 108 watts that is on for 1 minute? A, 1080, B, 60, C, 6480, D, 9642. If we look at this diagram, which we have so often used in the past, which has a circuit with a battery of 18 volt and a light bulb with a resistance of 3 ohms, which provides an ampere of 6 amps, we can determine the number of watts that is present in this circuit by using the formula of P is equal to I to the second power times R. If we execute this formula, we end up with 108 watts, which we have done in the past. Now, if we remember that 1 joule per second is equal to 1 watt, therefore 1 watt is equal to 1 joule per second. If we operate these numbers and we multiply the numbers of watt by 60 seconds, we come out with the number of joules that are being utilized, which in this case is 6,480 joules. So the answer to this question is C. So in conclusion, when dealing with single resistor direct current circuits, once 2 factors of the Ohm or Joule's laws are known, the third and fourth factor can be obtained by simple math. Thank you.